Great. So by the way, when Jen gave me this title, she also promised me an impression of Sam.
I've always wanted an excuse to put Samuel Jackson on my slides. So traditional switches that we have in today's SDN networks and in many legacy networks as well are largely stateless in the data plane. And essentially that means that a lot of the functionality in modern networks has to reside in the control plane, whether in a distributed one or in a central one. So in a software-defined network, the logically centralized control plane becomes a point at which you can program and implement state variables that are important for representing your application. And install in the underlying switches, in this case, let's say an OpenFlow switch, stateless rules that determine how packets that enter the switch should be processed. So here you might have a table that matches packets based on patterns in the packet header and takes simple actions like forwarding the packet or dropping it or modifying it. But the key point for this talk is that those rules are process packets the same way no matter what packets came before them. There's nothing dynamic taking place directly in the data plane that affects the forwarding of packets. And so this forces you into a sort of a two-tiered programming model where you have a stateless data plane that processes each packet independently. And if there is state, it's in very limited forms, such as traffic counters. And then a stateful control plane that has all sorts of variables in it that might represent the logic of your program and might, based on that logic, occasionally update the static rules that are installed in the data plane. And so the implication of that is that for some applications that do need to update state frequently, that forces a lot of events, or in particular a lot of packets, to go to the controller. Or more realistically, those kind of applications just never get built, because sending every packet or even a large fraction of packets to the controller is just a deal breaker in terms of performance, scalability, reliability, security, and so on. So the nice thing is that some of the emerging switches that are starting to come out are actually able to support state updates in the data plane at the level of individual packets. And so I want to look in this talk at what kinds of functionality that might enable and how we might program this next generation of switches. So just to put this in a little more context, imagine that the switch can have a simple key value store where packets, when they arrive, can be matched on a key and then have some amount of arithmetic and Boolean logic done to decide how that state value might be updated. And then the packet might be forwarded later on based on the value of that state. For example, in this case, because the value associated with the key is 100, that packet might be dropped. Future packets that arrive after it will potentially continue to update this value based on the previous value. So there are a bunch of different people looking at how to make it possible for switches to support these kinds of operations, and there are a number of programmatic interfaces to switches that are being proposed now. There's one called P4 that I and a group of other people in this room are involved in. There's another called Protocol Oblivious Forwarding, or POF. OpenState, and even Open vSwitch itself has certain forms of programmatic control over data plane state. And perhaps more importantly, in addition to state, there are a bunch of other features that are important for being able to manipulate state in flexible ways, including the ability to parse the packets in a programmable way so that you can put state in packet headers that might not normally have been there and interpret it later in the data plane, the ability to do simple arithmetic and Boolean operations on the packets as part of updating the state, and the ability to access other state in the switch itself, such as the depths of queues that are waiting to send packets or the current time. So if you combine all these things together, it becomes possible to implement a certain class of network functions directly in the data plane of commodity switches rather than in the controller, or as is more common today, in middle boxes. Now, this flexibility isn't arbitrary. You often can't do things that require reconstruction of byte streams out of packets, and you can't do arbitrarily complicated arithmetic and Boolean checks. So this wouldn't necessarily replace all things that are normally implemented in middle boxes. For example, we might not be able to do transcoding or compression and so on directly in the data plane. But it lets us do a whole bunch of things that would normally be off limits today. So what I want to do in the rest of this talk is two things. I want to walk you through one example application that we've built that exploits this capability. And then second, start to hint at some programming abstractions that might be useful going forward when the switches support these capabilities. So the first is a project called HULA that is a joint project with VMware and Barefoot, looking at how to take advantage of these programmable stateful updates in data planes to support load balancing directly in the data plane. So traffic engineering and load balancing is a very rich topic. It's been studied over many years, and it's done in many different ways. Here I just want to describe one particular way you might imagine doing it that is done in a distributed fashion, but directly in the data plane rather than in control plane software on the switches, let alone a central controller. So the basic idea here is we've got a network with a lot of path diversity, say a data center, and we've got traffic going between pairs of top of rack or TOR switches, potentially over multiple different paths. What we want to do is collect real-time information about the utilization of those paths and decide when a packet arrives which of the paths is the current best one and send the packets over that path. We don't want to do this on every single packet because that can lead to out-of-order packet delivery when a bunch of packets belong to the same flow. So we're going to do this at the level of so-called flowlets, group of packets that belong to the same TCP connection but are close together in time. So you want to force them to go on the same path rather than splitting them over different paths at the risk of them getting out of order. So we need to do three things. We need to collect statistics about the paths. I'm not going to go into a lot of detail about that, but I'll briefly touch on that. We need to group packets together that belong in the same flowlet, where the next packet in a flowlet should inherit the decision based on the previous one, independent of which path is currently best. And finally, we want to be able, when a new flowlet starts, to take that packet and associate it and the rest of the packets in that flowlet with the current best path. And that can be done with some simple tables directly in the data plane. And so I'm going to describe two different tables and how they relate to each other. The first one is going to keep track for a given top of rack destination switch. What is the current best hop, next hop to get to that destination? So here the table is indexed by the destination top of rack switch. And then stored there is the current best next hop to get along a path towards that destination and the current utilization of the downstream path from that current switch to that destination over that path. And we have this for every one of the top of rack switches. So this simple table can be updated in the data plane at packet timescales, and it can be done in two different ways. Right? One is when probes in the network give you information about the current performance of the downstream path, you can update this table entry if necessary. So what HULA does is the destination Tor switch will periodically send probes to all uplinks coming into it from other paths. And then when a switch receives that information, it'll look at the utilization of the link on which that probe was received and update the information in the table if necessary and propagate it onward to its own uplinks further upstream in the network. So when a probe comes in with an indication of a particular destination Tor switch and the utilization seen so far on that downstream path, that information can be compared against the path that's currently stored in the table. And if it's better than that path can be changed. So for example, if S3 is the best next hop right now and a probe comes in from S2 that indicates a better downstream path of the utilization of say 40%, that entry can be updated with the new next hop and the new downstream path utilization. Or if more information comes from S3 that indicates maybe its load has gone up or gone down, the information about the current best hop can be updated with new utilization statistics. Okay, so that's one thing. Then the data packets can also access this table to figure out right now what is the best next hop for me to use to reach a particular destination Tor switch. So the table can be written by the probes and can be read by regular data packets that need to figure out how they should be forwarded. Now, I mentioned earlier we don't really want to make that decision on a per packet basis. We want all packets in a little burst to be actually associated with the same decision. And so we can do that by maintaining a table of so-called flowlets. In this case, the index into the table is, say, a hash of the header fields in the packet, so that all packets from the same TCP connection get hashed the same way. And we can store information about the destination, the current time. This will be the timestamp of the last packet that hit this entry, and the next hop that was picked for this flowlet. So what's going to happen then? If a packet comes in, you're going to check the time, and if the time indicates that it was actually quite a long time ago since this entry was last updated, I'm free to use the current best information from the previous table I mentioned. But if the time elapsed is relatively tiny, I have to inherit the choice that's listed in this table, even if it's no longer the best choice. And that's part of making decisions at the flowlet basis. And then finally, whichever of those two next hops ends up being the one I pick, I now am going to actually forward the packet out that way. Okay. So just to recapitulate that, imagine a packet comes in. The first stateful table is going to indicate, let's say, based on the destination top of rack switch, what next hop is currently the best one. I'm going to look in the next table and figure out, well, am I actually allowed to use that one, or am I forced to use the one that the previous packets in my flowlet used? And so I'll look, based on the hash of the packet, I'll look at actually what the current timestamp is. If enough time has elapsed, I'm free to use the new best hop. Otherwise, I'm forced to inherit the old one. Yeah?
So does it mean, do you mean link utilization, or is it actually path utilization?
It's actually path utilization. Yeah, I kind of elided some details there, but let me actually.
So how does it get the path utilization?
So the destination Tor switch will send information about its incoming link utilization out each of its upstream links. That switch will now know the path utilization of that one hop path and store the best one it gets, to all in this case only one, in its table. Send it to the next uplink, including the minimum of the available bandwidth on now the two-hop path. So think of it as actually a path vector protocol taking place, or actually really distance vector protocol taking place, where as I go, I'm accumulating I guess in this case, the max utilization of the downstream path and picking the min among such paths. Does that make sense? Yeah. There's a detail there that matters, because doing this in the way I described, you can't really take a min over all paths. You're taking a min as you go. So if this current path, let's say the path via S3, got gradually worse, until I got a probe for a path that now looks better, I will still continue using that one, because I'm not keeping a full history of previous probes. I'm just keeping the current minimum I've seen, and if it starts to get worse, I won't have an opportunity to update it until new probes tell me about other paths that are now better. And that's one thing I'm going to come back to at the end. These schemes often have a lot of compromises because of the limitations of having to use constant state. And it'd be interesting to think, for a lot of algorithms, we think about what kind of approximation errors get introduced by that kind of operation. Yeah?
Do you worry about stability? Do you care about it at all? Like, because that's kind of been one of the dangers with any kind of distributed load balancing.
Yeah, definitely. I wasn't planning on talking about that here. There's some about this in the paper, but it's certainly a concern. This is, for people that have read the Conga paper that was at SIGCOMM a couple years ago, this is essentially a generalization of Conga. Conga dealt with 2-hop paths, and this is dealing with arbitrary paths and using programmable commodity switches rather than custom ASICs. So there's a lot of work in the Conga paper on stability that applies here as well. But it's a very reasonable concern. So the key point I wanted to mention here, though, is because we have stateful data planes today, it's possible to implement schemes like this directly in the data plane at line rate, so that you can make dynamic load balancing decisions on RTT timescales rather than on whatever control plane latency timescales you might have. And the more interesting point, perhaps, is not this one application, but that there's a whole host of other applications that we would never think of implementing directly in a network switch today that become possible once you can have relatively simple notions of state and state updates directly in the data plane. So what I want to do with the rest of the talk is just give a little bit of an overview of some work a number of us have been doing on how to make it easier for people to write these kinds of stateful applications, and then touch on some open research questions in stateful data planes. And so this is joint work with a number of people, some of whom are in this room today. So basically, the reason writing these applications can be difficult is, first of all, the interfaces that are provided to the switch are quite low level. There's multiple stages of match action processing and registers or arrays for maintaining the state. And we'd like to abstract above these hardware details to make it possible for people to write general reusable code. Also, these networks have many switches, and often we'd like to be able to support the ability to spread the state and the operations on that state over multiple switches as appropriate. Again, that's a gory detail you'd hope to shield the programmer from. And finally, there are often multiple applications, forwarding, monitoring, security applications, and so on, that you'd like to be able to write independently and combine together. And so in the Snap language, that's exactly what we try to do. We try to provide a higher level abstraction that's hardware independent, that gives the programmer the illusion they're writing a program for a network that is a single big switch that stores state, and to support composition of multiple applications that may access the same state variables. So for people that are familiar with the earlier work on Netcat, a common way of modeling a policy in a stateless network that can translate very nicely into OpenFlow rules is to think of a network policy as a function from a packet and its current location to a set of packets and their locations, where that function operates on the location of the packet and the header fields in the packet. So we start with one input packet at a particular location, and we have 0 packets if that packet was dropped, 1 packet potentially at a new location or with its header fields modified in the case of forwarding, or in the case of multicast, perhaps a set of packets each at a different location. So in stateful packet processing, we have to generalize this. And what we've done in this work is take Netcat and add some additional capabilities to be able to act on state and to write state. So essentially then, this function is a little more complicated now. Right? It has to be able to operate not only on an input packet, but on the current state of all the variables in the network. And it's going to produce not only a set of packets, but potentially modifications to the state in the network that will affect the processing of future packets that go through it. So I'll give you a simple example of a Snap program. And this is basically what we do is we model state as arrays that can be indexed on packet header fields. So this looks very much like C code, and that's somewhat intentional. It's very, very similar to that. And each of the things in red is an array indexed by 1 or more header fields in the packet. So to give a little more context, in this example, we're trying to detect DNS reflection attacks. So a DNS reflection attack happens when an adversary sends a spoofed DNS request to a bunch of open DNS resolvers in the hope that the victim, who is the owner of the spoofed IP address, will get a whole bunch of DNS responses directed at him for queries he never made. So what we do here in this application is whenever someone makes a DNS query, we keep track of it to make sure that when responses come back later, they were actually to requests that party sent in the first place. So the scene array is keeping track by client IP address and the DNS ID of the request that client sends, whether or not that client has actually sent a DNS query. If a response comes back to a particular IP address, this time now the potential victim is the destination, we're going to check, hey, was this query actually made by this party in the first place? And if not, we're going to keep track of how many times this client has received DNS responses for questions it never asked. And if that passes a threshold, we're going to say that we suspect this destination IP address as being the victim of a DNS reflection attack. And we'll take action at this point. Maybe alert a network operator, maybe drop the packets, maybe rate limit the packets. For our purposes, we don't care. So just notice here, this is just a bunch of code, looks like C, has a bunch of arrays. And now the challenge before us is we have to figure out which packets need to affect which state variables, where to put those state variables, and how to create routes through the network that make sure the relevant packets go through the relevant state in the correct order. And that's the problem we want to try to solve using the compiler. So the next step is that's just one of the applications. You could imagine there being others. In this case, I show a very small example where I just have a forwarding application that based on where traffic enters the network and where it's going, packets get forwarded out a particular exit point in the network. So a very simple forwarding policy. And then we'd like to be able to compose those together to do DNS reflection attack detection combined with packet forwarding. So packets not only need to be directed through the relevant state variables, but they need to go out of the network at the place the routing policy says they should go. Okay. So these are just two examples. We've implemented a whole bunch of other applications in Snap, drawing on a number of papers in the literature on security applications and so on. And many of these are monitoring or security applications. So in the last few minutes, I just want to say a few words about what the Snap compiler does. That's sort of where all the action is. So the problem the compiler now has to solve is we're given a bunch of Snap programs that have been combined together by the programmer. We need to somehow synthesize one canonical program that represents what all of these programs are trying to do. And then we need to distribute the state and generate the routes that will make sure all of those programs execute correctly in a distributed fashion over the switches in the network. Okay? So that's the problem the compiler has to solve. And the way we do that is the first thing we have to do naturally is look at dependencies between these state variables. And if you remember the program I had earlier, some of those elements in the array some arrays have to be accessed before others are. And so we need to make sure when packets visit those array elements, they visit them in the same order that the program requires. So the first thing we do is we analyze the state dependencies to figure out ordering constraints on the state variables. And then we need to identify what subset of packets, if any, need to go through what set of state variables. Some packets don't need to go through any state variables and can be routed any way we want. The others will have their routing constrained in some way to make sure they actually do traverse whatever switch might store that state variable. And then finally, we're going to need to generate the rules in the switches that actually correspond to that policy. And to do that, we select an intermediate representation of the Snap program to make it easier to do a lot of this analysis. That's called extended forwarding decision diagrams, extending previous work on extending binary decision diagrams. And then we, based on the output of our analysis, run a mixed and interlinear program to distribute the final result over the collection of switches. For people that have worked on middle box placement and traffic steering, our optimization problem will look very familiar. It's a very similar kind of problem. And then finally, we'll generate the switch level rules. So I just want to touch in the last few minutes on what an extended forwarding decision diagram is, because I think there might be interesting algorithmic issues here, both in supporting them and in looking at further generalizations of them. So forwarding decision diagram is an extension, as I mentioned, of binary decision diagrams. And here we extend it further to include stateful tests and stateful operations. It's going to allow us to take that sort of English text-like version of the Snap program and represent it in a canonical form. To take two such programs and step-by-step combine them together to generate another canonical representation of the composed program is going to make it possible for us to partition a program so that part of it can run on one switch, and then the next switch that gets the packet can take over and run its next step in the diagram. So here's what an extended forwarding decision diagram looks like. The nodes are tests on header fields or on state. The leaves are sets of actions that need to be performed on the packets that have satisfied all the tests leading up to it. The solid edges are true outputs, and the dotted edges are false. And there are three different types of tests, and I've shown them in a particular order. First is testing a field for a constant value, like destination equals 10.0.0.1. You could also test whether a field is equal to another field. That becomes particularly important when you merge two programs together by composition, where the same state variable might be accessed by two different programs based on different header fields. And we may have to know if those two header fields have the same value to know if those two programs are actually reading or writing the same state variable. We can't just look at the name of the variable being used as an index. We actually have to know whether the two different indices have the same value. And finally, the ability to test whether a state variable has a particular value. And we order them in this way, tests by value, tests by field, and tests on state variables to create a single canonical representation of any Snap program. So I won't go through the gory details for the DNS reflection example, but this just to show you that we can come up with a reasonably compact representation of the programs like the DNS reflection example. So the remaining challenge is to take this representation now and actually distribute the state variables, the checks, the tests, and so on over the switches in the network. And essentially what we do there is we take in the dependency graph that we've generated that indicates which state variables have certain dependencies, which packets need to go through particular state variables, and finally an estimate of the offered load that will figure out what fraction of the traffic that's entering the network will follow a particular set of state variables.
I have a question. Do XFDDs have similar properties to BDDs? Like there's a canonical form that you could take any one and put it in any XFDD?
Exactly. And in our case, what that means is that we put tests in a particular order, and we have to canonicalize an ordering, for example, of arrays. So if there's array 1, array 2, we'll pick an ordering of them so that there's always a consistent representation.
I'm surprised by the answer, because FDDs don't have the properties that others wants. So I'd be surprised if XFDDs do. There can be multiple different but equivalent representations of the same function as an FDD.
Is that just because of field orderings, or?
No, because of actions and tests and sort of relations between those.
Okay, I must be mistaken then. Dave, do you have a?
I withdraw the question.
Yeah, no, I thought that we'd picked a canonical ordering by the way we did the naming of the
I don't
test.
think you don't get equivalence from just, you can have two different functions that have different XFDD representations.
Okay.
Let's take it offline.
Okay. So when we actually, in the optimization problem, take in the dependency graph and the packet state mapping and the traffic matrix, and then the output is the state placement and the routing that would place the state, each piece of state on one particular switch in the network, routing that will visit the state variables in the appropriate order for the appropriate fraction of the traffic. And I just encourage you to see the paper for more details and experiments. So I'm just going to end by just a couple of notes on, I think, some interesting directions for future work. This is pretty early days in terms of reasoning about state in the data plane. And in Snap itself, there are a lot of things we don't support yet that we'd like to. In particular, the ability to assign a field in a packet based on the current value of a state variable so that we can carry state values from one hop to the next. We could do much more flexible things in terms of sharding of the array elements over multiple different switches, as well as state replication so that it's possible to actually have multiple copies of state in different locations, and faster compilation as well. And then I just wanted to close by saying the switches differ quite a lot in how much they can do in the data plane with regard to state. I glossed over that earlier, but there are limits on how much computational work you can do at line rate. And this is one of the reasons why the network functions you implement in the data plane have to be pretty simple. So there are limits on how much computation you can do per packet. There's different ways of representing these arrays or key value stores or hash tables. They each come with different limitations about how efficient they are in the representation, or whether you can create new entries, for example, in a key value store at line rate, or if that actually has to be done with some delay. And so I think there's a lot of opportunity, particularly here, to reason about different consistency models and different update policies in terms of what you can really do at line rate in hardware, and how to reflect that back to the programmer in reasonably high level ways. And also just to explore a much, much wider range of applications that can leverage this type of technology. And I'll end there, and if there's time, I'll take a couple questions. Yeah.
So I have a couple of questions, one on each part of the talk. So with respect to the load balancing work that you have described,
So Conga did this work where they were using flowlets, and you're basically using a similar idea, but for networks where the paths are longer. What a sequence of papers following Conga showed, one of which was our Rexford paper from last year's SIGCOMM, was that instead of using flowlets, which can have arbitrary sizes, if you used fixed size chunks of flows, our paper flow cell, in the degenerate case, you can imagine these being just packets getting spread across multiple paths, then you don't have to worry about any sort of load monitoring or balancing. You just spray these fixed sized units across multiple equal cost paths, and nothing fancy needs to happen within the network.
Okay.
And of course, this can lead to reordering, but you address that by having a reordering resistant stack or changing something in the hypervisor to do appropriate ordering of packets.
Okay.
So I was just wondering, like, given that there exist solutions that don't require stateful processing in the network that achieve similar goals, do you see load balancing being an important application for these stateful network elements? Do you think that?
Yeah, it's a good question. I'd be interested to chat more with you offline. One other thing we've been exploring with VMware is a variant of HULA that runs only on the ingress switch as a hybrid solution, because it's a lot easier to imagine having either the soft switch on the end host actually supporting these kind of operations while you're still using legacy hardware switches. So there are also middle grounds like that.
Right, so we precisely use the virtual switch in the hypervisor to essentially implement what this was doing.
And even having the programmatic access to the software switch can be really useful as a way to ease deployment for doing that. So another piece of work we're doing is looking at making it easier to write P4-like programs to run in OVS to make it easier to support those.
So my second question was about, I think you briefly hinted at it in your future directions for Snap. It seems like what you're doing is that you have these state variables that are located at specific locations in your network, and then you sort of cajole routing to go through those state variables, which is basically taking traffic to where state is located. Which I was wondering, from an architectural point of view, wouldn't it be better if you just let routing be and took state to where traffic is going currently?
Yeah, to be clear, we're doing both. We're doing a joint optimization of state placement and routing. So if the routing will be picked based on the state, and the state is placed based on the routing. It's not like we're optimizing one first and then the other. The MLIP that we have is doing a joint optimization of both.
But isn't routing being artificially constrained because of where state could possibly be located? I'm just wondering.
Sure, yeah, but there's no free lunch, right? If you need the traffic to go through that state. I mean, the state could be placed potentially on any switch. So it's just a question, if you have two different flows that would normally go on two different paths, and they both need to go through the same state variable, you'd be constraining the two to meet at some point so that they can.
Or you could replicate that state variable.
Well, this is related to the, exactly. And then replication is quite reasonable if it's read-only access. But if they're going to be doing updates to that state, and each of them need to be handled correctly in relation to that update, you have a problem. Yeah, and these are exactly the kind of questions we'd like to get at, because I think if you're willing to take a somewhat weak consistency for those updates, then it might be quite reasonable to replicate.
Right,
and then
not every packet would update a state. Maybe this would happen once per session or something.
Exactly, or it might be that using slightly out-of-date information is just inefficient and not incorrect. And these are exactly the kind of things that'd be nice to try to capture to be able to relax the placement criteria based on that. Yes, a really good question. Yeah.
Quick comment, as somebody who dabbles in verification, this worries me a lot around being able to, just around the time we are learning to reason about how to verify data planes, data plane just gets way more complicated. More concretely, can I just thinking about how to actually make this work? Can state be shared across two programs running in the network?
So we can have two array elements referred to in the same program, but they have to be done in ways that make sense. I mean, it's not arbitrary. There's certainly times we can throw up our hands and say that something isn't possible because of consistency problems.
But this seems like if two programs share state, it just seems like worse than, let's say, just from a verification or correctness perspective, it seems worse than race conditions. It seems worse than concurrency bugs, because an unrelated or a sister program can come along and update the state.
Yeah, it may very well be that in many settings it's not a sensible thing to do. That's certainly true. Yeah. As far as your question about verification, I'm trying to keep us all in business for a while. No, but seriously, all kidding aside, if you look at the DNS reflection example I mentioned, that application would be running somewhere. Right, it's just a question, do you want it running on the controller at great expense, or do you want it running in the data plane? And so you're right, I've taken a control plane verification question and made it a data plane one, but it's the same code.
Yes, I think that's why I asked about shared state between programs, right? So given just that program, which is isolated from other effects, so I can just verify that program and go home, right? Now there's state in the network, and if two separate programs can touch it,
Right, well, a sensible way to, completely agree, but a completely sensible way to do that would be one is writing it, the other's reading it. Right, I mean, I agree with you, arbitrarily having multiple parties writing the same state, you're going to have all sorts of difficulties, right?
Like the stack compiler could mangle the names so that each module had its own.
Yeah, so
If that's the desired semantics, clearly, yeah, but I think he's talking about a case where the person intended the operations, right? I mean, that's, I mean, yeah, Nate's completely right.
I guess even in that limited example, right, the writer, like to reason just about the correctness of the reader program, let's say there's a writer program and a reader program, and I want to reason about the correctness of the reader program.
Yeah.
But because this writer program runs kind of independently, I have no idea what state's going to show up.
Right. You'd have to understand that. It might,
what the inputs to the reader program are, and it may just get too strict to show that this reader program is correct under all possible inputs.
fair enough, fair enough.
And things like that.
But a good example, like in this case, if you know what IP addresses are suspected of being victims of an attack, another program might be doing some sort of operation, or another module of the same program doing operations based on that understanding, like deciding whether to drop or not drop. That would be a simple example. That doesn't seem too difficult to accept.
Sorry, just as a follow-up. So how different do you think would be like verifying networks with middle boxes, right? I mean, clearly there's a bunch of us looking at modeling and verifying networks with middle boxes. Do you envision it's going to be, so the way I thought of it as like, these are like lightweight middle box functions that could be implemented on top of switches, not like very fancy distributed state management systems.
Yeah.
So it doesn't seem like harder than that problem. I mean, that's a hard problem, but this doesn't seem harder than that problem.
And the tool just wants to pretend middle boxes don't exist. And
No,
put them
no,
out as
I was just thinking to your question, is the middle box verification problem you consider solved, or do you think we have a good handle on it already, and the same
I got to be in this mess too.
In general, I would say none. So in general, if you want to go down that path, I would say none of the verification problems are being solved. So that's so fine.
I would actually just we're having a discussion here. I would argue that data plane verification is almost close to solved at this point.
So the question I'd ask is the data plane verification problem solved for Microsoft, or is it solved for the general world? Like, I think
I'm actually going to call an executive timeout. This is algorithm, not verification. So this is a different workshop.
And I probably overstayed my welcome too.
One more question. So, do you think it can get to a point where you can generalize this so much that you only need the controller at the beginning of the network, or where you only want to change some policy, or for example for load balancing or for fault resilience or something like that? You can put some.
I think it's tricky to say that because, I mean, one thing that's not talked about here is like what happens when a link fails. I mean, there are various things. For example, you may need to rerun an incremental optimization to change the routes in a way that's coherent with the state placement after a link failure. And so some of that work is going to be difficult to do directly in the data plane. So I think there's still a place for the controller, at a minimum, dealing with traffic matrix and topology changes, and perhaps also with more fundamental issues that might arise, like the need to change the very set of modules you're composing in the first place. But it's a really interesting question. To what extent can you get the controller out of the loop otherwise?